Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of cars. Please like and subscribe for more restful content. Now, let's begin. The story of the automobile begins not with gasoline or pistons or rubber tires, but with a fundamental human longing that stretches back through millennia. It is the desire to move faster than our own legs can carry us, to traverse distances that would exhaust even the strongest among us, to conquer the friction and resistance that the earth places between one point and another. For most of human history, this longing was answered by the patient strength of animals. Horses, oxen, camels, and elephants became our partners in movement, extending our reach across continents and linking distant civilizations. But the dream of mechanical motion, of machines that could propel themselves without the need for living muscle, flickered in the minds of inventors and philosophers long before the technology existed to make it real. The earliest whispers of self-propelled vehicles appear in sketches and treatises from the Renaissance. Leonardo da Vinci, that inexhaustible genius of observation and imagination, drew designs for spring-powered carts in the late 15th century. These were elaborate clockwork mechanisms, wound tight with human effort and then released to roll forward under their own stored energy. They were toys of concept rather than practical machines, but they represented something profound. The idea that motion need not depend on ongoing animal or human exertion. The energy could be captured, stored, and released on demand. This notion would prove revolutionary, though it would take centuries to mature into something truly transformative. By the 17th century, natural philosophers were beginning to understand the fundamental principles that govern motion and energy. Isaac Newton's laws of motion, published in his Principia Mathematica in 1687, provided a mathematical framework for understanding how forces create acceleration and how mass resists changes in velocity. These laws would become the foundation for all mechanical engineering, including the development of vehicles. But understanding the principles of motion and actually harnessing a practical source of power to create sustained movement were two very different challenges. Wind and water had been captured for millennia to grind grain and pump water, but these forces were fixed in place, tethered to mills and dams. What was needed was a portable source of power, something that could be carried along with a vehicle and release its energy continuously as the vehicle moved. The answer, it turned out, lay in heat. More specifically, it lay in the ability to convert thermal energy into mechanical work. The science of thermodynamics, which would eventually explain why this conversion is possible and what its limits are, was still being developed in the 18th and 19th centuries. But practical engineers were already building machines that exploited heat's power to move pistons and turn wheels. The steam engine emerged as the first successful technology to accomplish this transformation. Water, when heated sufficiently, undergoes a phase change from liquid to gas, expanding dramatically in volume. This expansion, when contained and directed through carefully designed chambers and valves, can push against a piston or turn a turbine. The piston's linear motion can then be converted through connecting rods and cranks into rotational motion, which is ideal for driving wheels. Thomas Newcomen built the first practical steam engine in 1712, designed to pump water from coal mines in England. It was enormous, inefficient, and stationary, but it worked. James Watt improved upon Newcomen's design substantially in the latter half of the 18th century, introducing a separate condenser that greatly increased efficiency and making the steam engine a viable source of power for factories and eventually for transportation. By the early 1800s, steam engines were being mounted on wheeled carriages. These steam carriages were marvels of their age, huffing and clanking along roads at speeds that seemed miraculous compared to horse-drawn vehicles. Nicolas Joseph Cugnot, a French military engineer, built what is often considered the first self-propelled mechanical vehicle in 1769. It was a three-wheeled artillery tractor powered by a steam engine, and though it was slow and difficult to control, it demonstrated that a machine could indeed move itself and carry a load without any animal assistance. Yet steam power, for all its revolutionary impact on industry and rail transport, had significant limitations when applied to road vehicles. Steam engines require a boiler to heat water, a firebox to burn fuel, and substantial quantities of water itself. This makes them heavy and bulky. They also require time to build up pressure before they can operate, which means a steam vehicle cannot simply be started and driven away like a horse can be mounted and ridden. The inefficiency of early steam engines meant that much of the energy released by burning coal or wood was lost as waste heat rather than being converted into useful work. The laws of thermodynamics, gradually being formalized through the work of scientists like Sadi Carnot in the 1820s, explained why no heat engine could ever be perfectly efficient. Some energy must always flow from hot to cold and be dispersed as entropy, that measure of disorder and unavailable energy that increases in every real process. But even within these fundamental constraints, there was room for improvement, and inventors throughout the 19th century sought a more compact, more responsive, and more efficient means of converting fuel into motion. The critical breakthrough came with the realization that combustion did not need to occur in a separate firebox that heated water to make steam. Instead, fuel could be burned directly inside a cylinder, with the hot expanding gases pushing the piston directly. This concept, the internal combustion engine, would prove to be the key that unlocked personal mechanical transportation. The idea was not entirely new. Gunpowder had been pushing projectiles from cannons for centuries through the force of rapid combustion, but controlling combustion to produce smooth, continuous, repeatable cycles of power was an engineering challenge of extraordinary complexity. It required understanding the chemistry of fuels, the mechanics of valves and pistons, the timing of ignition, and the thermal management of an engine that would generate intense heat in concentrated spaces. The earliest experiments with internal combustion engines in the 17th century used gunpowder as fuel, which was far too violent and unpredictable for practical applications. By the mid-19th century, inventors were exploring liquid and gaseous fuels that could combust more controllably. Jean-Joseph Etienne Lenoir, a Belgian engineer working in France, built the first commercially successful internal combustion engine in 1860. It ran on coal gas mixed with air, ignited by an electric spark. The expanding hot gases pushed a piston, which turned a crankshaft, which could then drive machinery or wheels. Lenoir's engine was noisy and inefficient, converting only about 4% of the fuel's energy into useful work, but it represented a profound step forward. It was compact enough to be mounted on a vehicle, and in 1863, Lenoir built a car powered by his engine that successfully travelled a distance of several miles, though at a painfully slow pace. The transformation of the internal combustion engine from a crude experimental device into a practical source of power required understanding the precise choreography of events that must occur inside a cylinder to extract maximum work from burning fuel. This choreography is known as the engine cycle, and the most successful early design was the four-stroke cycle, developed independently by several inventors, but most effectively realized by Nicholas August Otto, a German engineer whose name would become synonymous with this fundamental operating principle. Otto's engine, perfected in 1876, established a pattern of operation that remains the foundation of most automobile engines, even today, more than a century and a half later. The four-stroke cycle divides the engine's operation into four distinct phases, each corresponding to one movement of the piston within the cylinder. To understand why this arrangement works so effectively, we must first consider what happens at the molecular level when fuel burns. Combustion is a chemical reaction, specifically a rapid oxidation reaction in which hydrocarbon molecules in the fuel combine with oxygen molecules from the air. This reaction breaks apart the chemical bonds in the fuel and oxygen and forms new bonds in the products of combustion, primarily carbon dioxide and water vapour. The key to combustion's usefulness as a power source lies in the fact that the new bonds formed in the products store less energy than the bonds that were broken in the reactants. The difference in energy is released as heat, which manifests as the rapid motion of the newly formed molecules. These hot, fast-moving molecules exert pressure on their surroundings, and it is this pressure that pushes the piston and creates mechanical work. In the first stroke of Otto's cycle, known as the intake stroke, the piston moves downward in the cylinder while an intake valve opens. This downward motion creates a partial vacuum, a region of lower pressure that draws in a mixture of air and fuel vapour. The fuel must be vaporized so that it can mix thoroughly with the air at the molecular level, creating a homogeneous mixture in which every oxygen molecule has access to fuel molecules. Early engines used simple carburetors for this purpose, devices that relied on the Venturi effect to draw liquid fuel into a stream of air and atomize it into fine droplets that quickly evaporated. The Venturi effect is a consequence of Bernoulli's principle, which describes how the pressure of a moving fluid decreases as its velocity increases. By forcing air through a narrowed passage, the carburetor creates a low-pressure zone into which fuel is drawn through a small jet, emerging as a fine spray. Once the cylinder is filled with the fuel-air mixture, the intake valve closes and the second stroke begins. This is the compression stroke, during which the piston moves upward, reducing the volume available to the gas mixture and consequently increasing its pressure and temperature. The relationship between pressure, volume, and temperature in a gas is described by the ideal gas law and its various derivative expressions. When a gas is compressed, work is done on it, and this work manifests as increased internal energy, which we perceive as a rise in temperature. The compression ratio, the ratio between the maximum and minimum volumes in the cylinder, is a critical parameter in engine design. Higher compression ratios generally lead to greater efficiency because they extract more work from each cycle of combustion, but they also create more extreme conditions of pressure and temperature that place greater stress on engine components and increase the likelihood of abnormal combustion events. At the end of the compression stroke, when the piston has reached the top of the cylinder and the fuel-air mixture is compressed to perhaps 1/8 or 1/10 of its original volume, a spark is introduced. In Otto's original engine, this spark came from an electric ignition system, a significant advancement over earlier engines that relied on flame or heated tubes to initiate combustion. The spark, a brief arc of electricity jumping across a small gap between two electrodes, provides the activation energy needed to initiate the combustion reaction. Even though the fuel and oxygen molecules are intimately mixed and would release substantial energy if they reacted, they do not spontaneously combust at room temperature because chemical bonds must first be broken before new ones can form. Breaking these initial bonds requires an input of energy, the activation energy, which the spark provides by heating a tiny region of the mixture to a temperature high enough that molecular collisions become violent enough to shatter existing bonds. Once ignition occurs, combustion spreads rapidly through the cylinder as a flame front, a thin boundary where the reaction is occurring. The flame front propagates outward from the spark plug at speeds that can reach dozens of meters per second, converting unburned mixture into hot combustion products. The temperature within the cylinder can exceed 2000 degrees Celsius, and the pressure can rise to 50 times atmospheric pressure or more. This is the power stroke, the third phase of the cycle, during which the expanding hot gases push the piston downward with tremendous force. The piston is connected to a crankshaft by a connecting rod, and as the piston moves downward, it rotates the crankshaft, converting the linear motion of combustion into the rotational motion needed to turn wheels. The crankshaft is a brilliantly simple mechanical device, an eccentrically shaped shaft that transforms reciprocating motion into continuous rotation, much as pedaling a bicycle converts the up and down motion of your legs into the spinning of the wheels. As the piston descends during the power stroke, the gases continue to expand and cool, their pressure gradually decreasing. By the time the piston reaches the bottom of its travel, much of the energy from combustion has been extracted, though the gases are still considerably hotter than atmospheric air and retain some pressure. Now the fourth and final stroke begins. An exhaust valve opens and the piston rises again, pushing the spent combustion products out of the cylinder and into the exhaust system. These exhaust gases, primarily carbon dioxide, water vapour and nitrogen, along with smaller amounts of carbon monoxide, unburned hydrocarbons and nitrogen oxides, carry away the waste heat that could not be converted into mechanical work. The laws of thermodynamics dictate that no heat engine operating between two temperature reservoirs can be more efficient than a theoretical ideal called the Carnot efficiency, which depends only on the temperatures of the hot and cold reservoirs. Real engines fall short of even this theoretical limit due to friction, incomplete combustion, heat loss through cylinder walls, and the time required for valves to open and close. After the exhaust stroke completes, the exhaust valve closes, the intake valve opens, and the cycle begins anew. In a multi-cylinder engine, the pistons are arranged so that their power strokes occur at different times, ensuring that the crankshaft receives a relatively continuous supply of force rather than discrete pulses. A four-cylinder engine might have its cylinders firing in a sequence such as 1, 3, 4, 2, with each cylinder at a different phase of its four-stroke cycle at any given moment. This arrangement smooths out the delivery of power and reduces vibration, making the engine more pleasant to use and reducing mechanical stress. Otto's four-stroke engine was a commercial success, manufactured in substantial numbers and used to power factories, workshops and machinery across Europe. It ran on coal gas initially, which limited its portability since gas had to be supplied through fixed pipes, much like modern natural gas. But the principles Otto established were applicable to any gaseous or easily vaporized fuel. The stage was set for the next crucial development, finding a liquid fuel with the right properties to power a truly mobile engine, one that could be carried on a vehicle and used anywhere without connection to external fuel supplies. That fuel would be petroleum, and its refinement and application would transform not only transportation, but the entire structure of industrial civilization. Petroleum, that thick dark liquid drawn from deep beneath the Earth's surface, had been known to humanity for thousands of years. Ancient civilizations collected it where it seeped naturally from the ground, using it as waterproofing for boats, as mortar in construction, and occasionally as medicine. But it was not until the mid-19th century that anyone thought to drill deliberately for petroleum or to refine it systematically into useful products. The first successful oil well was drilled in 1859 by Edwin Drake in Titusville, Pennsylvania, and it unleashed a cascade of industrial development that would reshape the global economy. Initially, the most valuable product refined from crude oil was kerosene, used for lighting lamps before electricity became widespread. Gasoline, a lighter and more volatile fraction that distilled off at lower temperatures, was initially considered a waste product, sometimes simply burned off or dumped into rivers. The chemistry of petroleum is complex and fascinating. Crude oil is a mixture of hundreds of different hydrocarbon compounds, molecules consisting primarily of hydrogen and carbon atoms bonded together in chains and rings of varying lengths. These molecules were formed over millions of years from the remains of ancient marine organisms, subjected to heat and pressure deep underground in the absence of oxygen. The lightest hydrocarbons, those with only a few carbon atoms, are gases at room temperature. Methane, with a single carbon atom bonded to 4 hydrogen atoms, and propane, with 3 carbons, exist as gases that we now use for heating and cooking. As the carbon chains grow longer, the compounds become liquids. Gasoline consists primarily of hydrocarbons with 5 to 12 carbon atoms, while kerosene and diesel fuel contain longer chains of 12 to 20 carbons or more. The heaviest fractions, with chains of 25 or more carbon atoms, are thick, viscous materials used for lubricating oils and asphalt. The refining process separates crude oil into these different fractions through distillation, a technique that exploits the fact that different molecules boil at different temperatures. When crude oil is heated in a tall distillation column, the lightest compounds vaporize first and rise to the top, where they cool and condense. Heavier compounds condense at lower levels, and the heaviest remain as residue at the bottom. This elegant separation process, refined and perfected over decades, allowed petroleum refiners to produce gasoline in quantity once demand for it began to emerge. And that demand came directly from the development of small, practical internal combustion engines that could run on this volatile liquid fuel. Gasoline proved to be an ideal fuel for internal combustion engines for several reasons. Its volatility meant it vaporized easily, mixing readily with air to form a combustible mixture. Its energy density, the amount of energy stored per unit of weight, was remarkably high. A single kilogram of gasoline contains approximately 46 megajoules of energy, enough to lift a 1 kilogram object to a height of nearly 5 million meters, if that energy could be converted with perfect efficiency into gravitational potential energy. Of course, real engines convert only a fraction of this chemical energy into useful work, but even at 20 to 30% efficiency, gasoline provided far more energy per kilogram than any practical alternative available in the late 19th century. Its liquid state at room temperature meant it could be easily stored and transported, yet it was volatile enough to form a combustible vapor at the modest temperatures found in engine intake systems. The development of practical gasoline engines proceeded through the work of several inventors, working largely independently in Germany during the 1880s. Gottlieb Daimler and Wilhelm Maybach developed a compact, high-speed engine that used gasoline as fuel. Unlike Otto's larger stationary engines, Daimler's design was small and light enough to be mounted on a vehicle. In 1885, Daimler attached his engine to a wooden bicycle frame, creating one of the first motorcycles. The following year, he and Maybach installed an improved version in a four-wheeled carriage, producing what could reasonably be called an automobile. The engine ran at 600 revolutions per minute, far faster than earlier engines, and this higher operating speed allowed it to produce more power from a smaller, lighter package. The relationship between engine speed and power output is straightforward. Power is the rate of doing work, and an engine that completes more combustion cycles per minute can deliver more energy per unit time, assuming each cycle produces a similar amount of work. Meanwhile, Carl Benz was pursuing his own path toward the automobile. Benz, a self-taught engineer with a passion for mechanical systems, designed and built a complete vehicle from the ground up, rather than adapting an engine to an existing carriage. His Motorwagen, completed in 1885 and patented in 1886, is often considered the first true automobile because it was designed as an integrated system specifically intended for personal transportation. The Benz Motorwagen had 3 wheels, with a single wheel in front for steering and 2 larger wheels at the rear, driven by the engine. The engine itself was a single-cylinder 4-stroke unit running on gasoline, producing about 2/3 of a horsepower at 400 revolutions per minute. This modest power output was sufficient to propel the lightweight vehicle at speeds approaching 15 kilometers per hour, roughly the pace of a trotting horse. The vehicle's design embodied numerous innovations that would become standard features. Benz developed an electrical ignition system that used a battery and spark coil to generate the high-voltage spark needed for combustion. He designed a carburetor that mixed gasoline vapor with air in controlled proportions, ensuring reliable combustion. He incorporated a simple but effective cooling system that used water circulating around the cylinder to absorb excess heat, preventing the engine from overheating and losing efficiency or sustaining damage. The mechanical components were connected through a series of gears and belts that transmitted power from the engine's crankshaft to the rear wheels, and a differential gear allowed the 2 drive wheels to rotate at different speeds when turning, preventing tyre scrubbing and mechanical binding. Benz's wife Bertha played a crucial role in demonstrating the vehicle's practicality. In 1888, without telling her husband, she and their 2 teenage sons drove the Motorwagen on a journey of more than 100 kilometers from Mannheim to Pforzheim to visit Bertha's mother. This was the first long-distance automobile trip in history, and it was not without difficulties. The vehicle required frequent stops to refill with water for cooling and to clean the fuel line, which became clogged with impurities. At one point, Bertha used her hatpin to clear a blocked fuel pipe and her garter to insulate a wire. She purchased fuel at pharmacies along the route, as gasoline was sold as a cleaning solvent. Despite these challenges, the journey succeeded, demonstrating that automobiles could be more than laboratory curiosities or short-distance novelties. They could be practical machines for transportation across meaningful distances. The final decade of the 19th century witnessed the automobile's transformation from experimental curiosity into a recognizable product that could be manufactured and sold to customers. This transition required not only technical refinements to make vehicles more reliable and easier to operate, but also the development of an entire supporting infrastructure that did not yet exist. There were no paved roads designed for motorized traffic, no filling stations where fuel could be purchased, no trained mechanics who understood how to repair these new machines, and no established body of knowledge about how to drive them safely. Every early motorist was simultaneously an explorer, an experimenter, and an advocate for a technology that many people regarded with suspicion or outright hostility. The technical challenges facing early automobile designers were formidable. Engines needed to become more powerful and more reliable while remaining light enough to be practical for small vehicles. The transmission systems that connected engines to wheels had to allow for variable speeds, since an engine operates efficiently only within a certain range of rotational speeds, while a vehicle needs to travel at vastly different speeds depending on conditions. Starting an engine required vigorous hand cranking, a physically demanding and sometimes dangerous task that could result in injury if the engine backfired and the crank spun violently backward. Steering mechanisms needed refinement to provide adequate control without excessive physical effort. Braking systems had to be developed that could safely stop a vehicle that might weigh several hundred kilograms and travel at speeds exceeding 30 kilometers per hour. The transmission problem was particularly vexing. An internal combustion engine produces useful power only when rotating within a specific range of speeds. Below this range, it stalls or runs roughly. Above it, mechanical stresses become excessive and efficiency declines. Yet a vehicle needs to start from rest, accelerate gradually, climb hills at reduced speed, and cruise efficiently at higher speeds on level ground. The solution involved placing a gearbox between the engine and the wheels, allowing the operator to select different gear ratios depending on conditions. In low gear, the engine might rotate several times for each rotation of the wheels, providing high torque for starting and climbing, but limiting speed. In high gear, the relationship might be nearly 1-to-1, allowing the engine's rotations to translate directly into wheel speed for efficient cruising. The mechanical implementation of this concept involved intricate arrangements of toothed gears that could be engaged or disengaged through the movement of sliding collars or other mechanisms. Early transmissions were difficult to operate, requiring careful coordination of throttle, clutch and gear lever, and producing harsh grinding noises if the gears were not properly synchronized in speed before engagement. The clutch itself, a device that could smoothly connect or disconnect the engine from the transmission, was essential for changing gears and for allowing the vehicle to remain stationary with the engine running. Most clutches operated on the principle of friction, using spring-loaded plates faced with friction material that could be pressed together to transmit force or separated to interrupt the connection. As automobile design matured, distinct approaches emerged in different countries, reflecting varying priorities and conditions. French manufacturers like Panhard et Levasseur established what became known as the Système Panhard, a layout that placed the engine at the front of the vehicle, used a friction clutch and gearbox to transmit power to the rear wheels through a drive shaft, and employed a steering mechanism that turned only the front wheels. This front-engine, rear-wheel drive configuration would dominate automobile design for most of the 20th century because it distributed weight relatively evenly, provided good traction, and separated the hot, noisy engine from the passenger compartment. The drive shaft, a long rotating tube that carried power from the transmission at the front to the differential at the rear axle, had to be carefully balanced and supported to avoid vibration. The differential, that ingenious device located at the driven axle, deserves special attention because it solves a problem that might not be immediately obvious. When a vehicle turns, the outer wheels must travel a greater distance than the inner wheels, yet both are connected to the same source of power. If they were rigidly connected to each other, one wheel would have to slip or skid, wasting energy and wearing tyres. The differential uses an arrangement of bevel gears that allows the two driven wheels to rotate at different speeds while still delivering power to both. When travelling straight, both wheels turn at the same rate and the differential's internal gears remain stationary relative to their housing. During a turn, these gears rotate, allowing speed to shift from one wheel to the other in precise proportion to the difference in the paths they must follow. While French and German manufacturers focused on refining gasoline-powered automobiles, other technologies competed for dominance. Electric vehicles powered by rechargeable batteries were quiet, clean, and easy to operate, requiring no gear changing or hand cranking. They were particularly popular among wealthy urban customers who valued refinement over range. The electric motor's characteristics complemented its use in vehicles beautifully. It could produce high torque even at low speeds, making gear changing unnecessary, and it could be controlled smoothly with simple rheostats that varied the current flow. Electric vehicles set early speed records and were favoured by many early motorists who found gasoline engines crude and temperamental. Yet batteries presented an insurmountable limitation. The energy density of even the best lead-acid batteries available at the turn of the century was roughly 1% that of gasoline. An electric vehicle might carry several hundred kilograms of batteries, yet achieve a range of only 50 or 60 kilometers under favourable conditions. Recharging required access to electricity, which was far from universal outside major cities and took many hours. As roads improved and the desire for longer distance travel grew, the electric vehicle's limitations became increasingly apparent. Steam-powered cars also continued to be manufactured, and some achieved remarkable performance. Steam engines could develop strong torque and operate quietly, and their external combustion meant that fuel could be burned continuously at optimal conditions rather than in rapid pulses, as in internal combustion engines. Despite these competitors, the gasoline-powered internal combustion engine gradually established its dominance through a combination of advantages. It offered better range than electric vehicles, quicker starting than steam cars, and improving refinement as engineering advanced. The infrastructure needed to support it began to emerge as demand grew. Pharmacies and general stores began stocking gasoline in addition to kerosene. Blacksmiths and bicycle mechanics learned to repair automobiles. Wealthy enthusiasts formed automobile clubs that advocated for better roads and established rules for operation. By 1900, automobile production was shifting from individual craftwork to small-scale manufacturing, with several dozen vehicles of a given model being built to common specifications. The age of personal motorized transportation had truly begun, though the automobile remained an expensive luxury accessible only to the wealthy. That situation would soon change dramatically through innovations in manufacturing that would make Henry Ford famous and transform the automobile into a mass-market product. As automobiles multiplied across the landscape during the 1920s and 30s, engineers turned their attention to refining the internal combustion engine itself, seeking greater power, improved efficiency, and smoother operation. The basic four-stroke cycle remained unchanged from Otto's original concept, but every component and every aspect of the combustion process became the subject of careful study and incremental improvement. Understanding how fuel burned inside the cylinder, how heat flowed through engine components, and how mechanical forces were transmitted through rotating and reciprocating parts allowed designers to push performance boundaries while improving reliability. One of the most significant areas of investigation concerned the compression ratio, that fundamental parameter describing how much the fuel-air mixture is squeezed before ignition. Higher compression ratios extract more work from each unit of fuel because they force the expanding combustion gases to push through a greater distance before the exhaust valve opens and releases them. The thermodynamic efficiency of an ideal Otto cycle engine increases directly with compression ratio, following a mathematical relationship that shows efficiency approaching but never quite reaching perfection as compression increases. In practical terms, raising the compression ratio from 6:1 to 8:1 might improve fuel efficiency by 10 or 15%, a substantial gain that translates into fewer stops for refueling and lower operating costs. However, higher compression ratios create a problem known as knock or detonation. Under normal combustion, the flame front initiated by the spark plug propagates smoothly across the combustion chamber, converting unburned mixture into hot products at a controlled rate. But when compression ratios rise too high, the heat and pressure generated during compression can cause portions of the fuel-air mixture distant from the spark plug to spontaneously ignite before the flame front reaches them. This uncontrolled ignition creates shock waves that bounce around the combustion chamber, producing the characteristic pinging or knocking sound and potentially damaging pistons, valves, and cylinder heads. The tendency of a fuel to resist knock depends on its chemical composition. Some hydrocarbons ignite more readily than others under compression, and the complex mixture of compounds in gasoline can vary considerably in its knock resistance. The solution came through chemistry. In the early 1920s, researchers discovered that adding small amounts of tetraethyl led to gasoline dramatically increased its octane rating, a measure of knock resistance. Leaded gasoline allowed engines to run at higher compression ratios without knock, improving both power and efficiency. For decades, tetraethyl lead was added to virtually all gasoline, enabling steady increases in engine performance. The compound worked by interfering with the chain reactions that lead to auto-ignition, essentially acting as a chemical brake on runaway combustion. Unfortunately, lead is highly toxic, and its widespread use in fuel led to environmental contamination and health problems that would not be fully recognised and addressed until the 1970s, when leaded gasoline began to be phased out in favour of cleaner alternatives. Engine cooling represented another critical area of development. Combustion temperatures inside cylinders can exceed 2000 degrees Celsius, far higher than most metals can withstand for extended periods. Some of this heat flows into the cylinder walls, cylinder head, and pistons, and must be removed continuously to prevent overheating and mechanical failure. Early engines used simple water jackets, passages cast into the engine block through which water circulated by natural convection. As the water near the hot cylinder walls heated up, it became less dense and rose, drawing cooler water from below. This thermosiphon effect provided adequate cooling for low-power engines running at moderate speeds, but more powerful engines required forced circulation using water pumps. The cooling system must maintain the engine within a specific temperature range. Too cold, and fuel vaporization becomes incomplete. Combustion efficiency drops, and oil becomes thick and sluggish, increasing friction. Too hot and lubricating oil breaks down. Metal parts expand excessively and can seize, and knock becomes more likely. Thermostats, simple mechanical valves that respond to temperature by opening or closing passages, regulate coolant flow to maintain optimal operating temperature regardless of outside conditions or engine load. The coolant itself is not pure water, but rather a mixture of water and antifreeze, typically ethylene glycol, which lowers the freezing point, raises the boiling point, and provides corrosion protection for the metal passages through which it circulates. Lubrication proved equally critical to engine longevity and performance. The rapid reciprocating motion of pistons within cylinders, the rotation of crankshafts and camshafts within bearings, and the sliding contact of valve stems within guides all generate friction that converts useful energy into waste heat and causes wear. Lubricating oil forms thin films between moving surfaces, separating them and allowing motion with minimal direct metal-to-metal contact. The oil must be viscous enough to maintain these protective films under the high pressures and temperatures found in engines, yet fluid enough to flow readily and not create excessive resistance to motion. Early engines used simple splash lubrication, with scoops on the crankshaft throwing oil upward to coat critical surfaces. More sophisticated designs employed pressurized oil systems with pumps that forced oil through drilled passages to bearings, then allowed it to drain back to a reservoir or sump at the bottom of the engine, where it could be pumped through again. Oil filters removed particulate contaminants generated by wear and combustion, extending both oil life and engine life. The development of motor oils with carefully formulated additive packages that improved viscosity characteristics across temperature ranges, prevented oxidation and sludge formation, and provided detergent action to keep surfaces clean represented a crucial but often overlooked contribution to automotive progress. The configuration of cylinders within an engine also evolved through experimentation and refinement. Early engines typically had 1, 2, or 4 cylinders arranged in a straight line, an inline configuration that was simple to manufacture and maintain. As power demands increased, more cylinders were added, leading to inline 6-cylinder and even 8-cylinder engines. Adding cylinders allows more power stroke per revolution of the crankshaft, smoothing out power delivery and reducing vibration. However, long inline engines become difficult to package within vehicle bodies, leading designers to explore alternative configurations. The V configuration, with two banks of cylinders arranged at an angle and sharing a common crankshaft, allowed more cylinders to fit in a shorter length. V8 engines became particularly popular in American automobiles, offering substantial power in a relatively compact package. The angle between the cylinder banks, typically 60 or 90 degrees, was chosen to balance considerations of compactness, crankshaft design, and firing smoothness. Each configuration has its characteristic sound and vibration signature, consequences of the timing of power strokes, and the balance of reciprocating and rotating masses. Engineers learned to calculate and minimize these vibrations through careful crankshaft design and the addition of counterweights that offset the forces generated by moving pistons and connecting rods. The decades between the two world wars witnessed remarkable progress in understanding what happened inside the combustion chamber during the brief moments when fuel ignited and burned. High-speed photography, pressure sensors, and careful chemical analysis of exhaust gases allowed researchers to peer into processes that occurred in milliseconds within sealed metal cylinders. This knowledge transformed engine design from an art based largely on trial and error into an engineering discipline grounded in physics and chemistry. Engineers learned that the shape of the combustion chamber, the location of the spark plug, the turbulence of the incoming air-fuel mixture, and dozens of other factors all influenced how efficiently fuel burned and how much power could be extracted. The combustion chamber's geometry proved surprisingly important. In early engines, the chamber was often just the space left above the piston when it reached the top of its stroke, with relatively little attention paid to its precise shape. Researchers discovered that combustion efficiency improved when the chamber was designed to promote turbulence, creating swirling motions that helped the flame front propagate quickly and completely through the mixture. Squish areas, regions where the rising piston nearly contacted the cylinder head, forced gases to accelerate toward the spark plug location just before ignition, enhancing mixing and speeding combustion. The ideal chamber shape balanced many competing requirements, promoting rapid combustion, resisting knock, minimizing surface area to reduce heat loss, and accommodating valves and spark plugs. Valve timing emerged as another critical variable. The simple description of the four-stroke cycle suggests that valves open and close precisely at the top and bottom of piston strokes, but real engines use more complex timing that accounts for the inertia of moving gases and the finite time required for valves to open fully. The intake valve typically begins opening before the piston reaches the top of the exhaust stroke and remains open past the bottom of the intake stroke. This valve overlap allows momentum from the exiting exhaust gases to help draw in fresh mixture, and the continued intake after the piston starts rising again takes advantage of the incoming mixture's inertia to pack slightly more charge into the cylinder. Similarly, the exhaust valve opens before the piston completes its power stroke, using the remaining pressure in the cylinder to begin expelling combustion products before the piston must push them out mechanically. The camshaft, that ingenious device that controls valve timing, consists of a rotating shaft with eccentric lobes that push against followers or rocker arms connected to the valves. As the shaft rotates, driven by the crankshaft through gears or chains, the lobes lift the valves at precisely timed intervals. The shape of each lobe determines not just when the valve opens and closes, but how quickly it moves and how long it stays open. Engineers discovered that different lobe profiles suited different operating conditions. Profiles that opened valves quickly and held them open longer improved breathing at high engine speeds, allowing more mixture to flow in and more exhaust to flow out. But these aggressive profiles could cause rough running at low speeds. The camshaft's design thus represented a compromise tailored to the engine's intended use. The carburetor, that device responsible for mixing fuel with air in appropriate proportions, evolved into a remarkably sophisticated instrument despite its apparent simplicity. The basic principle remained unchanged from early designs. Air flowing through a venturi created low pressure that drew fuel from a reservoir through calibrated jets, but maintaining the correct mixture ratio across the engine's full range of operating conditions required elaborate refinements. A cold engine needed a much richer mixture, more fuel relative to air, because fuel vaporized poorly at low temperatures. Starting required even more fuel. Acceleration demanded temporary enrichment to prevent hesitation. High-speed operation needed slightly different ratios than cruising. Multiple jets, chokes, accelerator pumps, and other features addressed these varying requirements, all operating mechanically without electronic controls. Materials science contributed substantially to engine improvement during this era. Pistons had to withstand extreme thermal and mechanical loads, while remaining as light as possible to reduce the forces generated by their rapid acceleration and deceleration. Aluminum alloys offered excellent strength-to-weight ratios and conducted heat well, helping to prevent hotspots that could trigger knock. But aluminum expands more than steel or cast iron when heated, requiring careful attention to clearances and piston design. Pistons were machined with slightly oval cross-sections and tapered profiles that would become circular and straight when they reached operating temperature. Piston rings, thin metal bands fitted into grooves around the piston, sealed the gap between piston and cylinder wall while allowing enough clearance for thermal expansion and lubrication. Crankshafts presented their own metallurgical challenges. These components endured enormous cyclical stresses as pistons pushed on them through connecting rods, subjecting them to complex combinations of bending, twisting, and compression that varied continuously as the crank rotated. Forged steel crankshafts, shaped by hammering or pressing heated steel into forms and then machined to final dimensions, offered superior strength compared to cast components. The journals, those smooth cylindrical surfaces where the crankshaft rotated within bearings, required extremely fine surface finishes to minimize friction and wear. Fillets, smoothly radius transitions between different sections of the shaft, prevented stress concentrations that could initiate fatigue cracks. The ignition system that provided the spark to initiate combustion also advanced considerably. Early systems used magnetos, self-contained devices that generated electrical current through the motion of magnets past coils of wire, then transformed this low voltage into the thousands of volts needed to jump the spark plug gap. Battery and coil ignition gradually replaced magnetos in automotive applications, offering more reliable starting and better performance at low engine speeds. The coil functioned as a transformer, using the magnetic field generated by current flowing through a primary winding to induce a much higher voltage in a secondary winding, with many more turns of finer wire. The timing of the spark had to advance as engine speed increased, occurring earlier in the compression stroke to allow time for combustion to develop fully. Mechanical advance mechanisms use centrifugal weights or vacuum diaphragms to adjust timing automatically. The Second World War accelerated automotive technology in unexpected ways, as military requirements pushed engineers to develop more powerful, more reliable engines that could operate under extreme conditions. Aircraft engines in particular advanced rapidly, and many innovations eventually found their way into automotive applications. The demands of war forced manufacturers to achieve levels of production that would have seemed impossible just years earlier, refining mass production techniques and quality control methods that would benefit peacetime manufacturing. When the war ended in 1945, pent-up consumer demand and improved manufacturing capabilities combined to launch a golden age of automotive expansion. The post-war years saw automobiles become truly universal in America and increasingly common in Europe and other industrialized regions. Highway systems expanded dramatically, with the United States beginning construction of its interstate highway system in 1956. These limited access roads, designed for sustained high-speed travel, encouraged the development of more powerful engines and more comfortable vehicles suited to long-distance cruising. Engine displacements grew larger, compression ratios increased with the availability of higher octane fuels, and features like automatic transmissions and power steering became increasingly common. The automatic transmission represented one of the most significant comfort and convenience improvements of this era. Manual transmissions required constant attention from the driver, who had to coordinate clutch, throttle, and gear lever for every change in speed. In heavy traffic or hilly terrain, this became tiresome and demanding. Automatic transmissions eliminated the clutch pedal and gear lever, using fluid couplings and planetary gear sets, controlled by hydraulic systems to select appropriate gear ratios based on vehicle speed and throttle position. The heart of most automatic transmissions was the torque converter, an ingenious fluid coupling device that could multiply torque at low speeds while allowing smooth engagement without the jerky engagement of mechanical clutches. Inside a torque converter, three main elements interact through transmission fluid. The pump, connected to the engine's crankshaft, spins and accelerates fluid outward through curved vanes. This high-velocity fluid strikes the turbine connected to the transmission input shaft, transferring energy and causing it to rotate. Between pump and turbine sits the stator, a stationary element with carefully shaped vanes that redirect fluid returning from the turbine back toward the pump. This redirection allows the fluid to strike the pump vanes in a direction that assists rotation, effectively multiplying the torque delivered to the transmission. At higher speeds, when torque multiplication is no longer needed, the stator freewheels and the converter acts as a simple fluid coupling. The entire device operates smoothly without any mechanical contact between engine and transmission, eliminating the harshness and wear associated with clutch engagement. During the 1950s and 60s, American automobiles grew larger and more powerful, with V8 engines displacing 5, 6, or even 7 litres becoming common. These engines prioritized torque and smooth power delivery over outright efficiency, reflecting cheap gasoline prices and cultural preferences for size and power. Chrome-laden styling emphasized presence and luxury. European manufacturers generally pursued different priorities, building smaller vehicles with more modest engines that emphasized fuel efficiency and nimble handling. These differences reflected both varying fuel costs, with gasoline far more expensive in Europe due to taxation, and different road conditions, with narrower streets and tighter spaces favoring compact vehicles. Engine technology continued advancing through incremental improvements. Better understanding of combustion chamber design, improved materials, more precise manufacturing, and enhanced lubrication all contributed to engines that produced more power from smaller displacements while lasting longer between overhauls. Compression ratios climbed to 10:1 or higher in premium engines. Overhead valve designs, with valves located in the cylinder head rather than in the engine block, became nearly universal because they allowed larger valves and more direct gas flow. Some high-performance engines adopted overhead camshafts, placing the camshaft directly above the valves it controlled, eliminating the pushrods and rocker arms needed in pushrod engines and allowing higher engine speeds. The relationship between engine speed and power output deserves closer examination. Power is the rate of doing work, measured in units like horsepower or kilowatts. An engine produces power by exerting force through distance over time. Each combustion cycle in a cylinder delivers a certain amount of energy as the expanding gases push the piston downward. An engine running at higher speed completes more cycles per minute, multiplying the power output even though each individual cycle may produce similar energy. This explains why small, high-revving engines can match the power of larger, slower-turning engines. However, higher speeds impose greater mechanical stresses and create more friction, requiring stronger components and more sophisticated engineering. The limitations of purely mechanical systems became increasingly apparent as engineers sought to optimize engine performance across wider operating ranges. Carburetors, for all their refinement, could not perfectly meter fuel for every possible combination of engine speed, load, temperature, and altitude. Fixed ignition timing curves could not ideally suit every operating condition. The solution would eventually come through electronics, but the technology needed for practical automotive electronic control systems did not yet exist. The transistor had been invented in 1947, and integrated circuits followed in the 1950s, but making these devices reliable enough and inexpensive enough for automotive use would require additional decades of development. Meanwhile, concerns about automotive emissions began emerging. The huge increase in vehicle numbers, particularly in cities like Los Angeles, with geographic features that trapped air pollution, created visible smog and measurable health impacts. Internal combustion engines emit various pollutants beyond the carbon dioxide and water vapour that represent complete combustion of hydrocarbon fuel. Incomplete combustion produces carbon monoxide, a colourless, odourless gas that interferes with blood's ability to carry oxygen. Unburned or partially burned hydrocarbons escape in exhaust gases. High combustion temperatures cause nitrogen and oxygen from the air to react, forming nitrogen oxides. These compounds, released into the atmosphere, undergo photochemical reactions in sunlight that create the brown haze characteristic of smog. California began implementing emission controls in the 1960s, forcing manufacturers to address pollution alongside performance and efficiency. The challenge of reducing emissions while maintaining performance forced engineers to reconsider fundamental assumptions about engine operation and exhaust treatment. The problem was complex because the conditions that minimized one type of pollutant often increased another. Carbon monoxide and unburned hydrocarbons result from incomplete combustion, which occurs when there is insufficient oxygen available or when combustion temperatures are too low. These emissions can be reduced by running the engine lean, with excess air beyond what is theoretically needed for complete combustion. However, the high temperatures associated with lean combustion favour the formation of nitrogen oxides, which form when nitrogen molecules from the air break apart and recombine with oxygen under extreme heat. The stoichiometric ratio, the precise air-to-fuel mixture that provides exactly enough oxygen to completely burn all the fuel, sits at approximately 14.7 parts, air to 1 part gasoline by weight. Richer mixtures with less air and more fuel produce excess carbon monoxide and hydrocarbons, but lower nitrogen oxides due to reduced combustion temperatures. Leaner mixtures with more air and less fuel reduce carbon monoxide and hydrocarbons, but increase nitrogen oxides. Optimizing emissions across all three pollutants simultaneously proved exceedingly difficult with carburetor-based fuel delivery systems that could not adjust mixture ratios with sufficient precision or speed to match constantly changing operating conditions. The solution emerged through catalytic converters, devices installed in the exhaust system that use chemical catalysts to convert pollutants into less harmful substances. A catalyst is a material that facilitates a chemical reaction without being consumed in the process. Platinum, palladium, and rhodium, precious metals with unique surface properties, can catalyze reactions that break down nitrogen oxides into nitrogen and oxygen, while simultaneously oxidizing carbon monoxide and unburned hydrocarbons into carbon dioxide and water. These reactions occur on the surface of the catalyst material, which is typically applied as a thin coating on a ceramic honeycomb structure, with thousands of tiny passages through which exhaust gases flow. For catalytic converters to function effectively, they must reach temperatures of several hundred degrees Celsius, which occurs naturally after a few minutes of engine operation as hot exhaust gases flow through them. The three-way catalytic converter, developed in the 1970s, could simultaneously address all three major pollutants, but only if the engine operated at or very near the stoichiometric ratio. Deviations of even a few percent in either direction dramatically reduced conversion efficiency. Maintaining such precise control required abandoning carburetors in favour of electronic fuel injection systems that could monitor exhaust composition and adjust fuel delivery many times per second. Electronic fuel injection had existed in various forms since the 1950s, used primarily in expensive sports cars and aircraft engines. These early systems used complex mechanical hydraulic controls or primitive electronic components that were expensive and sometimes unreliable. The development of microprocessors in the 1970s finally provided the computing power needed for sophisticated engine management at acceptable cost. A microprocessor, a complete computer processor fabricated on a single integrated circuit chip, could execute thousands of calculations per second, reading inputs from numerous sensors and adjusting fuel injection timing and duration accordingly. The oxygen sensor, installed in the exhaust stream ahead of the catalytic converter, provided the critical feedback needed for precise mixture control. This sensor generates a small voltage that changes sharply depending on whether the exhaust contains excess oxygen, indicating lean operation, or lacks oxygen, indicating rich operation. The engine control computer reads this voltage and adjusts the fuel injection pulse width, the duration that injectors spray fuel, to maintain operation at the stoichiometric ratio. This closed-loop control system constantly oscillates slightly rich and slightly lean around the ideal mixture, making corrections many times per second based on oxygen sensor readings. Fuel injectors themselves are precisely engineered valves controlled by electromagnetic solenoids. When the control computer sends an electrical pulse to an injector, the solenoid opens a spring-loaded valve and fuel under pressure sprays through a carefully designed nozzle that atomizes it into fine droplets. The longer the pulse duration, the more fuel is delivered. Early systems used one or two injectors that sprayed fuel into the intake manifold, where all cylinders drew from a common plenum. More sophisticated multi-point injection systems used individual injectors for each cylinder, mounted close to the intake valves, allowing more precise control and better fuel distribution. Electronic control extended beyond fuel delivery to ignition timing as well. Mechanical and vacuum advanced mechanisms were replaced by electronic ignition systems, where the control computer determined the optimal spark timing for every operating condition based on inputs from crankshaft position sensors, airflow sensors, coolant temperature sensors, and throttle position sensors. The computer could store complex timing maps in memory, developed through extensive testing to optimize power, efficiency, and emissions across the full range of engine speeds and loads. Knock sensors, which detected the characteristic vibrations caused by detonation, allowed the computer to retard timing if knock occurred, protecting the engine while allowing more aggressive base timing. The transition to electronic engine management occurred gradually through the 1980s, as costs decreased and reliability improved. Carburetors persisted on less expensive vehicles into the early 1990s, but eventually disappeared entirely as emissions regulations tightened and the advantages of electronic control became overwhelming. The computer could compensate for altitude changes, adjust for engine wear, adapt to different fuel qualities, and provide diagnostic capabilities that simplified troubleshooting and maintenance. Malfunction indicator lights on the dashboard alerted drivers to problems, and technicians could retrieve diagnostic trouble codes that identified specific sensor or system failures. These electronic systems transformed the automobile from a purely mechanical device into a complex integration of mechanical, hydraulic, electrical, and computational systems. The engine no longer operated according to fixed mechanical linkages and calibrations, but responded dynamically to constantly changing conditions under the guidance of software algorithms. This fundamental shift opened new possibilities for optimization, but also created new dependencies and complexities. Understanding an automobile now required knowledge not just of thermodynamics and mechanical engineering, but also of electronics, software, and control theory. The automobile had entered the digital age. While electronic controls improved the efficiency and reduced the emissions of conventional gasoline engines, researchers and engineers also explored alternative engine configurations and fuel cycles that might offer inherent advantages. One of the most significant alternatives was the diesel engine, named after Rudolf Diesel, a German engineer who developed it in the 1890s as a more efficient rival to the gasoline engine. Diesel's engine operated on fundamentally different principles than Otto's four-stroke gasoline engine, achieving ignition through compression alone rather than using a spark plug. And this difference conferred both advantages and limitations that would shape its applications for more than a century. The diesel cycle begins similarly to the Otto cycle, with the piston drawing in air during the intake stroke. However, unlike a gasoline engine, no fuel enters during intake. The cylinder fills with pure air, which has important implications for what happens next. During the compression stroke, the piston compresses this air to much higher pressures than in a gasoline engine, typically reaching ratios of 15:1 or even 20:1. Compressing a gas increases its temperature, and at these extreme compression ratios, the air temperature rises above the auto-ignition temperature of diesel fuel, typically exceeding 500 degrees Celsius. Near the end of the compression stroke, fuel is injected directly into the cylinder through a high-pressure injector. The fuel, sprayed as a fine mist into the intensely hot compressed air, ignites spontaneously without any spark. Combustion occurs gradually as fuel continues to be injected, with the rate of fuel injection controlling the rate of combustion and thus the power output. This differs fundamentally from a gasoline engine, where the entire fuel air charge is present before ignition and burns relatively rapidly once the spark initiates combustion. The diesel engine's ability to control power output by varying fuel quantity rather than by throttling air intake eliminates pumping losses associated with drawing air through a partially closed throttle valve, contributing to superior efficiency. The thermodynamic efficiency advantages of diesel engines stem from their higher compression ratios and their operating cycle. The theoretical efficiency of any heat engine increases with the temperature difference between its hot and cold reservoirs, and the extreme compression in diesel engines creates very high peak temperatures. Additionally, diesel engines always operate with excess air, running lean compared to gasoline engines that must maintain stoichiometric ratios for catalytic converter operation. This lean operation ensures complete combustion and contributes to efficiency. Real diesel engines commonly achieve thermal efficiencies of 40% or higher compared to 30% or less for typical gasoline engines, meaning more of the fuel's energy is converted into useful work rather than waste heat. However, diesel engines face their own set of challenges. The high compression ratios require much stronger, heavier engine construction to withstand the extreme pressures and forces. The fuel injection system must deliver fuel at very high pressures, often exceeding 2000 bar in modern engines, requiring robust and precisely manufactured injectors and pumps. Diesel fuel itself is less volatile than gasoline, which is advantageous for safety and storage, but makes cold starting difficult. At low temperatures, diesel fuel can become thick and gel, while the high compression ratios make cranking the engine over require more powerful starter motors. Glow plugs, electrical heating elements installed in the combustion chambers, preheat the air on cold starts to facilitate ignition. Diesel engines produce different emissions than gasoline engines. The lean combustion and high temperatures favour nitrogen oxide formation, while the nature of diesel combustion, with fuel injected into already burning zones, tends to produce particulate matter, tiny solid particles of partially burned fuel and carbon that appear as black smoke when excessive. These particulates pose health risks when inhaled and became a major focus of diesel emission control efforts. Modern diesel engines employ multiple strategies to address these emissions, including exhaust gas recirculation that routes some exhaust back into the intake to lower combustion temperatures and reduce nitrogen oxides, and diesel particulate filters that trap solid particles in a ceramic filter that is periodically regenerated by burning off the accumulated soot. For many decades, diesel engines were primarily used in trucks, buses, ships, and industrial equipment, where their efficiency advantages, durability, and ability to produce high torque at low engine speeds outweighed their greater weight and noise. Diesel fuel, a heavier fraction from petroleum refining than gasoline, was widely available and initially less expensive. In Europe, where fuel prices were higher due to taxation, diesel-powered passenger cars achieved significant market share beginning in the 1980s. Advanced injection systems and careful engine design reduced the noise and vibration that had long characterized diesel engines, making them more acceptable for passenger car use. Another alternative engine concept that attracted periodic interest was the rotary engine, most successfully developed by Felix Wankel in Germany during the 1950s. The Wankel engine abandoned pistons and cylinders entirely in favour of a triangular rotor that orbited within an oval housing. As the rotor spun, its three sides sequentially created expanding and contracting volumes that drew in fuel-air mixture, compressed it, allowed it to be ignited and expand, and then expelled the exhaust. This rotating motion eliminated the reciprocating forces of conventional engines, allowing smoother operation and very high power output relative to engine size and weight. The rotary engine's elegance and compactness made it attractive for applications where space and weight were critical. Mazda became the primary manufacturer to seriously pursue rotary engines for automotive use, producing sports cars powered by rotary engines from the 1960s onward. However, the rotary engine faced persistent challenges. The combustion chamber's elongated shape was far from ideal, resulting in incomplete combustion and high emissions. The seals between the rotor tips and housing were difficult to make durable, often wearing rapidly and allowing compression loss. Fuel consumption was relatively poor compared to conventional engines of similar power output. These limitations prevented the rotary engine from displacing piston engines despite its theoretical advantages. Two-stroke engines represented yet another alternative that found widespread use in motorcycles, small engines for lawn equipment and chainsaws, and some specialized applications. The two-stroke cycle completed intake, compression, power, and exhaust in just 2 piston strokes rather than 4, potentially doubling power output for a given engine size. However, two-stroke engines typically mixed oil with fuel for lubrication and suffered from incomplete separation of intake and exhaust processes, leading to poor fuel economy and high emissions. They remained largely confined to applications where simplicity and high power-to-weight ratio outweighed efficiency and emissions concerns. The energy crises of the 1970s marked a turning point in automotive history, forcing a fundamental reassessment of priorities that had favoured power and size over efficiency. When oil-producing nations imposed embargoes and dramatically raised prices, fuel that had been cheap and abundant suddenly became expensive and sometimes scarce. Long lines formed at filling stations, rationing was implemented in some regions, and consumers who had enthusiastically purchased large vehicles with thirsty engines suddenly sought smaller, more economical alternatives. This crisis accelerated trends toward lighter vehicles, smaller engines, and more sophisticated approaches to extracting maximum efficiency from every unit of fuel consumed. Weight reduction emerged as one of the most direct paths to improved fuel economy. A lighter vehicle requires less energy to accelerate and less energy to maintain speed against rolling resistance and air drag. Automotive engineers had long understood this principle, but had prioritized other considerations when fuel was cheap. Now manufacturers scrutinized every component, seeking opportunities to reduce mass without compromising safety or durability. Steel remained the primary structural material, but thinner sheets with carefully designed reinforcements replaced heavier uniform sections. High-strength steel alloys allowed further reductions in thickness while maintaining strength. Aluminum, with roughly one-third the density of steel, found increasing use in engine blocks, wheels, and some body panels despite its higher cost. Aerodynamics received renewed attention as engineers recognized that air resistance increases with the square of velocity, becoming the dominant force resisting motion at highway speeds. The power required to overcome air drag follows a cubic relationship with speed, meaning that doubling speed requires 8 times the power to maintain that speed against air resistance. Reducing the drag coefficient, the dimensionless number that quantifies how streamlined a shape is, directly improved fuel economy at speed. Earlier automobiles had featured upright, boxy styling with sharp edges and exposed components like mirrors and door handles that disrupted airflow. Design studios began using wind tunnels to test clay models and refine shapes that allowed air to flow smoothly over, under, and around vehicles with minimal turbulence. Flush-mounted windows, carefully shaped bumpers integrated into body contours, underbody panels that smoothed airflow beneath the vehicle, and attention to how air exited from behind the vehicle all contributed to reducing drag. Even seemingly minor details like the angle of the windshield or the shape of side mirrors affected the overall drag coefficient. The most aerodynamically refined vehicles achieved drag coefficients below 0.3, compared to 0.4 or higher for typical earlier designs. This 25% reduction in drag translated directly into reduced fuel consumption at highway speeds, with no compromise in interior space or practical utility. Engine downsizing accompanied these efforts, with manufacturers offering smaller displacement engines that used advanced technology to maintain adequate performance despite reduced size. Turbocharging represented one of the most effective technologies for extracting more power from smaller engines. A turbocharger uses a turbine wheel mounted in the exhaust stream to capture energy from hot exhaust gases that would otherwise be wasted. This turbine spins a compressor wheel mounted on the same shaft, and the compressor forces additional air into the engine's intake system. By increasing the density of the intake charge, more fuel can be burned per cycle, effectively increasing the engine's displacement without actually making it physically larger. The physics underlying turbocharging relates to the fact that engine power is fundamentally limited by how much air-fuel mixture can be burned per unit time. Normally aspirated engines, those without turbochargers or superchargers, draw in air at atmospheric pressure and thus can only fill their cylinders to atmospheric density. A turbocharged engine packs more air molecules into the same volume, allowing proportionally more fuel to be added while maintaining proper air-fuel ratios. This increases power output substantially. A well-designed turbocharger system might allow a 2-litre engine to produce power comparable to a 3-litre naturally aspirated engine, while consuming less fuel during normal driving when the turbocharger is not boosting pressure significantly. However, turbocharging introduces complexities. The turbine and compressor operate at extremely high rotational speeds, often exceeding 100,000 revolutions per minute, requiring precision bearings and careful lubrication. The compressed air becomes heated by the compression process, reducing its density and potentially causing knock, so intercoolers were developed to cool the compressed air before it enters the cylinders. Turbo lag, a delay in power delivery when the throttle is opened suddenly, occurs because time is required for exhaust flow to accelerate the turbine from idle to full boost. Engineers work to minimize this lag through careful turbocharger sizing and advanced control systems. Transmission technology also contributed to efficiency improvements. Traditional automatic transmissions with 3 or 4 forward gears gave way to designs with 5, 6, or eventually 8 or more ratios. Additional gears allowed the engine to operate closer to its most efficient speed across a wider range of vehicle speeds. The lowest gear provided strong acceleration from rest, while the highest gear allowed relaxed cruising at highway speeds with the engine turning slowly and consuming minimal fuel. The wide ratio spread between lowest and highest gears required intermediate ratios to avoid excessively large steps between gears that would cause abrupt changes in engine speed during shifts. Overdrive gears, ratios where the output shaft rotates faster than the input shaft, became common for highway cruising. In overdrive, the engine turns slower than the transmission output, reducing friction losses and allowing the engine to operate at more efficient speeds. The term overdrive reflects the fact that the drive ratio is numerically less than 1:1, overdriving the wheels relative to engine speed. Combined with taller axle ratios, overdrive transmissions significantly reduced engine speeds during steady cruising, where most highway fuel consumption occurs. Lock-up torque converters addressed one of the automatic transmission's inherent inefficiencies. Traditional fluid couplings slip continuously, with the turbine always rotating slightly slower than the pump, and this slip represents wasted energy converted to heat in the transmission fluid. A lock-up clutch mechanically connects pump and turbine once cruising speed is reached, eliminating slip and improving efficiency by several percent. The lockup engages smoothly through careful hydraulic control and disengages automatically when the driver accelerates or slows, reverting to fluid coupling operation when the smoothness and torque multiplication of the converter are beneficial. Manufacturers also reconsidered auxiliary systems that consumed engine power. Air conditioning compressors, power steering pumps, alternators, and water pumps all drew power from the engine through belts and pulleys. More efficient designs, variable displacement compressors that adjusted their output based on cooling demand, and eventually electrically driven accessories that operated independently of engine speed, all contributed to reducing parasitic losses. Every watt of power saved from accessories was a watt available for propelling the vehicle or simply not needed from fuel combustion. As the 20th century drew toward its close, concerns about automotive emissions evolved beyond local air quality to encompass global climate change. Carbon dioxide, the inevitable product of burning any carbon-based fuel with complete combustion, had long been considered harmless because it is non-toxic and naturally present in the atmosphere. However, accumulating scientific evidence demonstrated that increasing atmospheric carbon dioxide concentrations were contributing to global warming by enhancing the greenhouse effect, the process by which certain gases trap heat radiated from Earth's surface. Unlike pollutants that could be addressed through catalytic converters or filters, carbon dioxide reduction required burning less fuel, making efficiency improvements not just economically attractive, but environmentally imperative. This realization prompted renewed interest in hybrid vehicles that combined internal combustion engines with electric motors and batteries. The concept was not new. Experimental hybrid vehicles had been built as early as the beginning of the 20th century, and various prototypes appeared periodically over the decades. However, making hybrids practical required advances in battery technology, power electronics, and control systems that only matured in the 1990s. The fundamental advantage of hybrid systems lies in their ability to recover energy during braking that would normally be wasted as heat in brake friction, store it temporarily in batteries, and use it to assist acceleration or power the vehicle at low speeds where internal combustion engines are least efficient. Regenerative braking represents one of the hybrid vehicle's key innovations. When a conventional vehicle slows, friction brakes convert the kinetic energy of motion into heat, warming the brake rotors and pads, but accomplishing nothing useful beyond the necessary deceleration. In a hybrid vehicle, the electric motor can operate as a generator during braking, with the wheels driving the motor rather than the motor driving the wheels. This generates electrical current that charges the batteries while simultaneously creating resistance that slows the vehicle. The kinetic energy of motion thus transforms into stored electrical energy rather than waste heat, improving overall efficiency by capturing energy that would otherwise be lost. The internal combustion engine in a hybrid vehicle can be optimized differently than in a conventional car. Because the electric motor provides additional power during acceleration and can propel the vehicle alone at low speeds, the gasoline engine can be smaller and calibrated to operate most efficiently within a narrower range of speeds and loads. In some hybrid designs, the engine shuts off completely when the vehicle stops or travels slowly, eliminating fuel consumption during idling and reducing emissions during the stop-and-go driving common in urban environments. When power demand increases, the engine restarts seamlessly, often so smoothly that occupants barely notice the transition. Toyota's Prius, introduced in Japan in 1997 and in other markets soon after, became the first mass-produced hybrid vehicle to achieve significant commercial success. Its powertrain combined a gasoline engine with 2 electric motor generators in a sophisticated configuration that allowed the vehicle to operate in electric-only mode, gasoline-only mode, or with both power sources contributing simultaneously. A planetary gear set, the same type used in automatic transmissions, mechanically coupled the engine and motors in a way that allowed continuous variation of the speed relationship between them, eliminating the need for a conventional stepped transmission. This system, which Toyota called hybrid synergy drive, demonstrated that hybrid technology could be reliable, practical, and economically viable. Battery technology posed the greatest challenge for hybrid vehicles. Conventional lead-acid batteries, adequate for starting conventional vehicles and powering accessories, were too heavy and lacked sufficient energy density for storing and delivering the substantial power needed in hybrids. Nickel metal hydride batteries offered better energy density and power delivery characteristics, becoming the standard choice for early production hybrids. These batteries could withstand thousands of charge-discharge cycles and operated safely across a wide temperature range. However, the battery pack still represented a significant weight penalty and occupied valuable cargo space. The control systems managing energy flow between engine, motors and batteries required sophisticated algorithms implemented in powerful microprocessors. The system had to decide moment by moment whether to run on electricity, gasoline or both, when to charge the batteries using the engine or regenerative braking, and how to balance various competing priorities including efficiency, performance, battery longevity and emissions. These decisions occurred continuously based on inputs from dozens of sensors monitoring vehicle speed, acceleration demand, battery state of charge, engine temperature, and many other variables. The seamless integration of mechanical, electrical, and computational systems represented a remarkable engineering achievement. Despite their complexity, hybrid vehicles demonstrated clear efficiency advantages. The best hybrids achieved fuel consumption figures 50% better than comparable conventional vehicles in urban driving, where their advantages were greatest. Highway driving showed smaller improvements because steady-speed cruising, where regenerative braking offers no benefit and the engine already operates efficiently, plays to the strengths of conventional powertrains. Nevertheless, the overall efficiency gains were substantial, and hybrid technology represented the most significant advancement in automotive efficiency since the introduction of electronic fuel injection and emission controls. Other manufacturers developed their own hybrid systems, exploring different configurations and control strategies. Some emphasize performance rather than efficiency, using electric motors to supplement engine power for sports cars that combined impressive acceleration with acceptable fuel economy. Plug-in hybrid vehicles, which appeared later, featured larger battery packs that could be recharged from the electrical grid, allowing extended all-electric driving ranges before the gasoline engine needed to activate. These vehicles offered some advantages of pure electric vehicles, while eliminating range anxiety by retaining the combustion engine as backup. The success of hybrid vehicles validated electric propulsion for automotive applications and accelerated development of the power electronics, motors and batteries that would be essential for eventual pure electric vehicles. It also demonstrated that consumers would accept and even embrace new automotive technologies if they offered clear benefits. The hybrid era represented a transitional phase, bridging conventional internal combustion powertrains and the electric vehicles that many believed would eventually dominate transportation. Yet hybrids continued to offer practical advantages in applications where pure electric vehicles faced limitations, ensuring their continued relevance even as battery technology improved. The pursuit of ever greater efficiency and lower emissions eventually led engineers to reconsider the most fundamental aspects of internal combustion engine operation. Variable valve timing systems represented one breakthrough that allowed engines to adapt their breathing characteristics to different operating conditions. Traditional engines used fixed camshaft profiles that opened and closed valves according to unchanging patterns, forcing compromises between low-speed torque, high-speed power, fuel economy, and emissions. What worked well at low engine speeds often performed poorly at high speeds, and vice versa. Variable systems could adjust valve timing continuously, optimizing performance across the engine's entire operating range. The simplest variable timing systems altered the relationship between crankshaft position and camshaft position using hydraulically actuated mechanisms that could rotate the camshaft slightly relative to its drive gear. Advancing the intake camshaft caused intake valves to open earlier and close earlier, improving high-speed breathing and power. Retarding it delayed opening and closing, enhancing low-speed torque and emissions. The engine control computer commanded these changes based on engine speed, load, and other factors, continuously optimizing valve timing. More sophisticated systems independently controlled intake and exhaust camshafts, providing even greater flexibility. Some engines could adjust timing over ranges exceeding 50 degrees of crankshaft rotation, dramatically transforming their operating characteristics. Even more advanced systems varied not just timing, but also valve lift, the distance valves opened. Low engine loads require only small amounts of air, yet valves in traditional engines open fully on every cycle, regardless of need. This forces the engine to throttle the intake, creating a partial vacuum that wastes energy, as the pistons must work against reduced pressure during the intake stroke. By reducing valve lift at light loads, variable lift systems allowed engines to control airflow through the valves themselves rather than through a throttle plate, eliminating pumping losses and improving efficiency substantially. Some systems offered continuously variable lift across a wide range, while others switched between 2 or 3 discrete lift profiles. Cylinder deactivation technology took this concept further by completely shutting off fuel and spark to some cylinders when full power was not needed. A V8 engine cruising on the highway might operate on only 4 cylinders, with the other 4's valves held closed so they simply compressed and expanded trapped air without consuming fuel or producing power. The active cylinders worked slightly harder, operating at more efficient loads, while the deactivated cylinders contributed no power but also imposed minimal friction since their valves remained closed and no combustion occurred. Transitions between full and reduced cylinder operation had to be managed carefully to avoid noticeable jolts or vibrations, requiring sophisticated control of fuel injection, spark timing, and transmission operation. Direct fuel injection represented another significant advancement. Earlier multi-point injection systems sprayed fuel into the intake ports where it mixed with incoming air before entering the cylinders. Direct injection placed the injector directly in the combustion chamber, spraying fuel at high pressure directly into the cylinder during the compression stroke. This offered several advantages. The vaporizing fuel absorbed heat from the compressed air, cooling it and reducing the likelihood of knock, which allowed higher compression ratios. Fuel could be stratified, with a rich mixture near the spark plug for reliable ignition surrounded by leaner mixture, or even pure air elsewhere in the chamber, improving efficiency at light loads. The precise control over injection timing and spray pattern enabled new combustion strategies. Gasoline direct injection systems required fuel pressures much higher than port injection, often exceeding 100 bar, necessitating high-pressure fuel pumps and robust injectors. The injector nozzles featured multiple precisely angled holes that created spray patterns optimized for the combustion chamber shape. Injection could occur during intake, during compression, or in multiple pulses, with the timing and duration varied according to operating conditions. Some engines use stratified lean combustion at light loads for maximum efficiency, then switched to stoichiometric homogeneous combustion at higher loads for power and catalytic converter compatibility. Turbocharging became nearly universal in gasoline engines as manufacturers sought to reduce displacement while maintaining power. Smaller turbocharged engines could match or exceed the power of larger, naturally aspirated engines, while consuming less fuel during normal driving when boost was minimal. Advanced turbocharger designs with variable geometry turbines adjusted their internal passages to optimize performance across engine speeds, reducing lag and improving responsiveness. Twin-scroll turbine housings separated exhaust pulses from different cylinders to reduce interference and improve efficiency. Some engines use 2 turbochargers in series, with a small turbocharger providing quick response at low speeds and a larger one contributing at higher speeds for maximum power. The combination of these technologies produced engines that would have seemed impossible just decades earlier. A modern 2-litre turbocharged 4-cylinder engine with direct injection, variable valve timing, and sophisticated controls might produce over 300 horsepower, matching engines twice its size from earlier eras, while achieving fuel economy that would have been remarkable for a much smaller engine. Specific power outputs, measured in horsepower per litre of displacement, reached levels once associated only with exotic racing engines. Yet these highly stressed engines proved remarkably reliable, often exceeding 200,000 kilometres between major repairs when properly maintained. Transmission technology continued advancing as well. Continuously variable transmissions eliminated fixed gear ratios entirely, using steel belts or chains running between variable diameter pulleys to provide infinite ratio variation within their operating range. The engine could operate at its most efficient speed regardless of vehicle speed, with the transmission adjusting seamlessly to match conditions. Dual-clutch transmissions combine the efficiency and driver control of manual gearboxes with the convenience of automatics, using 2 clutches to alternate between odd and even gears, pre-selecting the next ratio before actually shifting. This allowed extremely rapid shifts with no interruption in power delivery. The internal combustion engine, refined through more than a century of development, reached extraordinary levels of sophistication. Modern engines burned fuel more completely, extracted more work from each combustion event, wasted less energy to friction and parasitic loads, and adapted their operation to suit instantaneous requirements with precision that would have astounded earlier engineers. They met emission standards so stringent that their exhaust contained lower concentrations of some pollutants than the ambient air they drew in. Yet even as these technologies matured, a fundamental transition was beginning that would challenge the internal combustion engine's dominance for the first time in over a century. The electric vehicle, which had competed with gasoline-powered automobiles at the dawn of the automotive age, before fading into obscurity, began a remarkable resurgence in the early 21st century. Advances in battery technology, particularly the development of lithium-ion batteries with far superior energy density compared to earlier chemistries, finally made electric vehicles practical for everyday use with acceptable range and performance. Unlike the internal combustion engine, with its thousands of precisely coordinated moving parts, complex fluid systems, and intricate thermal management requirements, the electric motor offered elegant simplicity. Electrical energy flowing through coiled wires created magnetic fields that exerted force on permanent magnets or electromagnets, producing smooth, quiet rotation with minimal maintenance requirements. The fundamental physics underlying electric motors had been understood since the 19th century. When current flows through a conductor in the presence of a magnetic field, the conductor experiences a force perpendicular to both the current direction and the field direction. By arranging multiple coils on a rotating shaft, called the rotor, and surrounding them with stationary magnets or coils, called the stator, this force can be harnessed to create continuous rotation. The torque produced depends on the current flowing through the coils and the strength of the magnetic field. Unlike internal combustion engines that must reach certain minimum speeds before producing useful power and deliver maximum torque only within narrow speed ranges, electric motors can produce their full torque from zero speed, providing immediate response and strong acceleration without need for complex transmissions. Several types of electric motors found application in vehicles, each with distinct characteristics. DC motors, which run on direct current, were used in early electric vehicles and some industrial applications because of their simple control characteristics. However, they required mechanical brushes to deliver current to the rotating coils, and these brushes wore out and generated electrical noise. AC induction motors, which run on alternating current, eliminated brushes entirely. The stator coils created rotating magnetic fields that induced currents in the rotor, which then interacted with the fields to produce torque. These motors were robust and reliable, but required sophisticated power electronics to generate the multi-phase alternating current needed for optimal control. Permanent magnet synchronous motors became increasingly common in modern electric vehicles. These motors used powerful rare earth magnets, typically made from neodymium iron boron alloys, embedded in the rotor. The stator coils created rotating magnetic fields that pulled on these permanent magnets, producing very high torque density and excellent efficiency. The term synchronous indicated that the rotor rotated in perfect synchronism with the rotating field, unlike induction motors where some slip occurred. Control electronics precisely regulated the timing and magnitude of currents flowing through the stator coils, adjusting them thousands of times per second to optimize torque production and efficiency across varying speeds and loads. The battery pack represented the most critical and expensive component of an electric vehicle. Lithium-ion batteries stored energy through reversible chemical reactions involving lithium ions moving between positive and negative electrodes through an electrolyte. During discharge, lithium ions flowed from the negative electrode, typically made of graphite, through the electrolyte to the positive electrode, typically a lithium metal oxide compound, while electrons flowed through the external circuit to power the motor. During charging, an external voltage reversed the process, driving lithium ions and electrons back to restore the original chemical state. These reactions occurred at voltages around 3 to 4 volts per cell, requiring hundreds of individual cells connected in series to achieve the several hundred volts needed for vehicle propulsion. Energy density remained the fundamental challenge. Even the best lithium-ion batteries stored only about 2% as much energy per kilogram as gasoline. An electric vehicle requiring a 50 kilowatt-hour battery pack to achieve reasonable range might carry 300 to 500 kilograms of batteries, a substantial weight penalty. However, electric drivetrains converted electrical energy to mechanical work far more efficiently than internal combustion engines converted chemical energy to work. While gasoline engines typically achieve 25 to 35% efficiency, electric motors and their associated electronics commonly exceeded 90% efficiency. This meant that despite the battery's lower energy density, the overall energy consumption per kilometre could be competitive with or better than gasoline vehicles. Battery thermal management proved critical for performance, longevity, and safety. Lithium-ion batteries operated best within a relatively narrow temperature range, typically 15 to 35 degrees Celsius. Too cold and their internal resistance increased, reducing available power and capacity. Too hot and degradation accelerated, shortening lifespan and potentially creating safety risks. Electric vehicles incorporated elaborate cooling systems using liquid coolant or refrigerant to maintain optimal battery temperatures. During rapid charging or hard acceleration, when batteries generated significant heat, active cooling prevented overheating. In cold climates, battery heating systems brought packs up to operating temperature. Charging infrastructure emerged as both an enabler and a constraint for electric vehicle adoption. Unlike gasoline vehicles that could refuel in minutes at ubiquitous filling stations, electric vehicles required hours to recharge from standard household outlets. Level 2 charging stations, operating at higher voltages and currents, reduced charging times to several hours, making overnight home charging practical. DC fast charging stations delivering 100 kilowatts or more could replenish significant range in 20 to 30 minutes, approaching the convenience of gasoline refueling for long-distance travel. However, installing charging infrastructure required substantial investment in equipment and electrical grid capacity. The absence of engine noise and vibration created entirely new acoustic environments inside electric vehicles. Without combustion pulses, mechanical valve train clatter, or exhaust rumble to mask other sounds, wind noise, tyre noise, and small squeaks or rattles became more noticeable. Manufacturers invested in additional sound insulation and structural refinement to maintain quiet cabins. Some added synthetic sounds, both inside the cabin to provide feedback about acceleration and outside to warn pedestrians of approaching vehicles that were otherwise nearly silent at low speeds. The change in sensory experience was profound, dividing opinion between those who appreciated the serenity and those who missed the auditory feedback they associated with driving. Regenerative braking became even more important in electric vehicles than in hybrids. By recovering energy during deceleration and returning it to the battery, electric vehicles extended their range substantially. Skilled drivers learned to modulate acceleration and braking to maximize energy recovery, treating each trip as an efficiency challenge. Some vehicles offered strong regenerative braking that allowed one-pedal driving, where releasing the accelerator pedal provided enough deceleration for most situations, using friction brakes only for final stops or emergency braking. This reduced brake wear dramatically, with brake pads sometimes lasting the vehicle's entire service life. The transition from internal combustion to electric propulsion forced reconsideration of vehicle architecture at the most fundamental level. Gasoline-powered vehicles had evolved around the constraints imposed by their powertrains. Engines required substantial space, generated significant heat and noise, vibrated noticeably, and needed access to air for combustion and cooling. Transmissions, drive shafts, exhaust systems, and fuel tanks all demanded accommodation within the vehicle structure. Electric vehicles eliminated many of these constraints while introducing new ones, enabling designers to reimagine how automobiles could be configured and how interior space could be utilized. The elimination of a large engine block opened possibilities for different proportions and packaging. Electric motors, being far more compact than engines of equivalent power, could be positioned almost anywhere. Some designs placed motors at the front or rear, maintaining familiar layouts. Others integrated motors directly into the wheel hubs, eliminating the need for half shafts and allowing more flexible suspension design. Multiple motor configurations became practical, with some vehicles using separate motors for front and rear axles or even individual motors for each wheel, enabling sophisticated torque vectoring that could distribute power between wheels to enhance handling and stability beyond what mechanical differentials could achieve. Battery packs, being flat assemblies of cells, lent themselves to mounting beneath the passenger compartment floor. This low, central placement lowered the vehicle's centre of gravity substantially, improving handling and reducing rollover risk. The structural battery pack could form part of the vehicle's chassis, contributing to overall rigidity. Tesla pioneered this skateboard architecture, where the batteries and electric motors formed a complete rolling chassis that could accept different body styles. The approach simplified manufacturing and allowed the same basic platform to support sedans, SUVs, or trucks, with relatively minor modifications to the upper body structure. The absence of a hot engine simplified cooling requirements while introducing new thermal management challenges. Electric motors and power electronics generated heat that needed dissipation, but at much lower rates than combustion engines. However, maintaining battery temperature proved more demanding than cooling engines because batteries were sensitive to both heat and cold, and the thermal mass of a large battery pack made temperature changes slow. Sophisticated thermal management systems circulated coolant through the battery pack, sometimes sharing cooling circuits with motors and electronics. sometimes using dedicated systems. Heat pumps, which could both heat and cool using the same hardware by reversing refrigerant flow, provided efficient climate control for both the cabin and the batteries. Range anxiety, the fear of running out of charge far from a charging station, remained the primary psychological barrier to electric vehicle adoption despite continuously improving battery capacity. Real-world range depended heavily on driving conditions, ambient temperature, and use of climate control systems. Highway driving at high speeds consumed energy rapidly due to aerodynamic drag, while stop-and-go city driving, which stressed gasoline engines, actually favoured electric vehicles through regenerative braking. Cold weather reduced battery capacity and required energy for heating, potentially cutting range by 30 or 40%. Hot weather demanded air conditioning and increased battery cooling needs. Accurate range prediction required sophisticated algorithms that considered topography, traffic conditions, driving style, and weather. Charging time and infrastructure availability shaped usage patterns fundamentally differently than gasoline refueling. Most electric vehicle owners charged at home overnight, beginning each day with a full battery, a convenience impossible with gasoline vehicles. This made electric vehicles particularly well suited to people with regular commuting patterns and home charging capability. For those without home charging, such as apartment dwellers or those parking on streets, public charging infrastructure became essential. Workplace charging, destination charging at shopping centres or restaurants, and fast charging networks along highways all contributed to a complex ecosystem quite different from the simple model of driving to a gas station when the tank ran low. Fast charging presented both opportunities and challenges. The power levels required to charge large battery packs quickly, often exceeding 200 kilowatts and approaching 350 kilowatts in the latest systems, placed substantial demands on electrical infrastructure. At these power levels, a charging session might draw as much electricity as a dozen homes simultaneously. Utilities had to manage this load and ensure adequate grid capacity. The batteries themselves faced stress from rapid charging, which generated heat and caused more rapid degradation than slower charging. Battery management systems carefully controlled charging rates, balancing speed against longevity and safety, sometimes reducing charging power as the battery approached full capacity. The environmental implications of electric vehicles extended beyond their zero tailpipe emissions. Manufacturing batteries required substantial energy and involved mining lithium, cobalt, nickel, and other materials with their own environmental and social impacts. The electricity used to charge vehicles came from grids with varying generation mixes, from heavily coal-dependent systems with high carbon intensity to grids dominated by hydroelectric, nuclear, or renewable sources. Life cycle analyses that accounted for manufacturing emissions, electricity generation emissions, and end-of-life recycling showed that electric vehicles typically produced lower total emissions than gasoline vehicles over their lifetimes, with the advantage increasing as electricity grids incorporated more renewable generation. Battery recycling emerged as both an environmental imperative and an economic opportunity. Lithium-ion batteries retained significant value even when their capacity degraded below what vehicles required. Packs no longer suitable for automotive use could serve in stationary energy storage applications for many additional years before final recycling. The materials themselves, particularly lithium, cobalt, and nickel, were valuable enough to justify recovery and reprocessing. Several companies developed recycling processes that could reclaim over 90% of battery materials, potentially creating closed-loop supply chains that reduced the need for new mining. However, recycling infrastructure was still developing, and methods varied in their energy requirements and material recovery rates. The user experience of electric vehicles diverged from conventional automobiles in subtle but meaningful ways. The instant torque delivery created acceleration characteristics that felt more responsive, even in modestly powered vehicles. The lack of gear changes meant smooth, uninterrupted acceleration from rest to highway speeds. Over-the-air software updates could improve performance, add features, or refine charging algorithms without visiting service centres. The simplicity of the drivetrain, with fewer fluids to change and no spark plugs, timing belts, or exhaust systems to maintain, reduced service requirements dramatically. Yet the batteries remained a source of concern regarding longevity and replacement cost, even as data from early adopters suggested degradation was slower than initially feared, with many vehicles retaining 85 to 90% capacity after hundreds of thousands of kilometres. As the automotive industry moved deeper into the 21st century, the convergence of electric propulsion, advanced batteries, sophisticated software, and autonomous driving technologies began to reshape fundamental assumptions about personal transportation. The automobile, which had represented freedom, independence, and personal expression for more than a century, was being reconsidered not merely as a different type of machine, but as a node in larger transportation networks, potentially shared rather than individually owned, increasingly automated rather than directly controlled. This transformation, still unfolding and contested, reflected technological capabilities that earlier generations could scarcely have imagined, alongside persistent questions about what would be gained and lost in the transition. Autonomous driving technology progressed through incremental steps, each adding capabilities while highlighting remaining challenges. Early driver assistance systems offered features like adaptive cruise control that maintained safe following distances, and lane-keeping assistance that provided gentle steering corrections to prevent unintended lane departures. These systems relied on radar sensors to detect vehicles ahead and cameras to recognize lane markings, processing this information through algorithms that made simple decisions about throttle, braking, and steering inputs. They functioned well under ideal conditions on highways, but required constant human supervision and readiness to intervene. More advanced systems incorporated additional sensors, including LiDAR, which used laser pulses to create detailed three-dimensional maps of surrounding environments with precision far exceeding human vision in many conditions. Ultrasonic sensors detected nearby objects during parking maneuvers. High-definition cameras captured traffic signals, signs, pedestrians, and other road users. Fusing data from these diverse sensors required substantial computational power and sophisticated software that could interpret complex, sometimes contradictory information in real time. The challenges multiplied in adverse weather when sensors became obscured, in construction zones where normal rules didn't apply, and in urban environments with unpredictable pedestrian behaviour and complex intersections. The progression from driver assistance to full autonomy involved levels of capability carefully defined by industry standards. Level 2 systems could control steering and speed simultaneously, but required continuous human attention. Level 3 allowed the driver to disengage under certain conditions, but demanded readiness to resume control when requested. Level 4 promised full autonomy within defined operating domains, such as specific geographic areas or road types, with no need for human intervention within those boundaries. Level 5, the ultimate goal, would match human driving capability across all conditions, eliminating the need for traditional controls entirely. Progress through these levels proved slower than optimistic early predictions, as edge cases and unusual situations revealed how much implicit knowledge and judgment human drivers employed. Machine learning and artificial intelligence became central to autonomous driving development. Rather than attempting to program explicit rules for every possible situation, engineers trained neural networks on vast datasets of driving scenarios, allowing systems to learn patterns and appropriate responses through exposure to millions of examples. These networks, inspired loosely by biological neural systems, consisted of interconnected layers of artificial neurons that processed inputs through weighted connections, adjusting those weights during training to minimize errors between predicted and actual correct responses. The resulting systems could recognize pedestrians, predict vehicle movements, and make driving decisions with superhuman consistency, yet they occasionally failed in ways that seemed inexplicable, misclassifying objects or missing obvious hazards that any human would immediately recognize. The safety implications of autonomous vehicles sparked intense debate. Proponents noted that human error caused the vast majority of accidents, and even imperfect autonomous systems might eventually surpass average human performance, potentially saving thousands of lives annually. Critics questioned whether society would accept machine-caused accidents, even if they occurred less frequently than human-caused ones, and worried about liability questions, cybersecurity vulnerabilities, and ethical dilemmas around how systems should behave in unavoidable collision scenarios. The testing and validation process required to demonstrate safety convincingly remained unclear, as proving statistical superiority demanded exposure to billions of kilometers of real-world driving across every conceivable condition. The potential restructuring of transportation systems around autonomous vehicles extended beyond individual car ownership to encompass shared fleets, on-demand mobility services, and integration with public transit. If vehicles could summon themselves when needed and operate continuously ferrying different passengers, individual ownership might become economically inefficient for many people. Urban parking requirements could shrink dramatically if vehicles didn't spend most of their time sitting idle. Traffic flow might improve through vehicle-to-vehicle communication and coordinated behaviour. However, these benefits assumed widespread adoption and raised questions about equity, privacy, and the social implications of eliminating millions of driving jobs, while fundamentally altering patterns of urban development that had organised themselves around personal vehicle ownership. The internal combustion engine, which had powered transportation for well over a century and evolved through countless refinements into machines of extraordinary sophistication, faced an uncertain future in this transformed landscape. Stricter emissions regulations, improving battery technology, falling costs for electric drivetrains, and governmental policies favouring or mandating electric vehicles all pressured manufacturers to accelerate their transitions away from gasoline and diesel power. Some announced timelines for ending production of new combustion engine vehicles entirely within the next decade or two. Yet the existing fleet of billions of vehicles would persist for decades more, and applications requiring long-range, rapid refuelling, or operation in extreme environments continue to favour liquid fuels. Synthetic fuels produced from renewable electricity, water, and captured carbon dioxide offered one potential path for continuing to use internal combustion engines while achieving carbon neutrality. These e-fuels could theoretically drop into existing vehicles and infrastructure with minimal modifications, leveraging the enormous installed base of engines and filling stations. However, the process of synthesizing liquid fuels from electricity was inherently inefficient, losing substantial energy in conversion, making direct use of electricity in battery vehicles far more efficient from an energy perspective. Economic viability depended on abundant, cheap, renewable electricity and would likely limit e-fuels to niche applications where batteries faced practical limitations. Hydrogen fuel cells represented another alternative, using stored hydrogen gas that reacted with oxygen in an electrochemical process to produce electricity, water vapour, and heat. Fuel cell vehicles offered refueling times comparable to gasoline vehicles and achieved ranges exceeding most battery electric vehicles. However, hydrogen production, compression, storage, and distribution presented formidable challenges. Most hydrogen came from natural gas reformation, a process that generated carbon dioxide, while electrolysis using renewable electricity was expensive and energy intensive. The high pressures required for practical storage, typically 700 bar or more, raised safety concerns and infrastructure costs. Fuel cells themselves remained expensive due to their platinum catalysts and demanding manufacturing requirements. Looking back across the arc of automotive history from those first tentative experiments with steam power through the mature sophistication of modern vehicles, the story that emerged was one of continuous refinement, punctuated by occasional revolutionary transitions. The internal combustion engine had proven remarkably adaptable, improving its efficiency, power, and cleanliness through countless innovations while maintaining its fundamental operating principles largely unchanged. It had enabled personal mobility on a scale that transformed societies, economies, and landscapes for better and for worse. Whether the transition to electric propulsion and autonomous operation would prove equally transformative, and what new challenges and opportunities it would create, remained to be discovered by future generations, who would live with the consequences of choices being made in the present moment.